Basis for students taking notes pretty well too.
Yeah, although if you have slides and you make them available, then the slides are available as
The
notes.
prospect of available slides means I don't really have to pay attention in class and take notes. I never get around to downloading.
They never get that kinesthetic experience of taking notes, which actually helps them remember.
It does. It does. It does. But, you know,
But mostly I
it's
like
hard enough to get them to take notes, period. So,
Well, I flipped my electronics class, so actually I have all the lectures very condensed on
so do you do the full lecture beforehand? Or do you do just a, because one way I've seen of doing it is doing just a sort of an introduction to the concepts.
No, so I do the full content is there. It's fast, right? Because when you're it's basically a PowerPoint and I write on top of it. But
Okay.
you know, I'm just pointing things out with a laser pointer. Yeah, you could do this like that.
Yeah.
And circling things occasionally, but so you know, I go through an hour and a half an hour usually.
Mm-hmm.
But then I often repeat it in class and then ask questions. And I don't have any great. I don't think that everybody watches the videos. Certainly not beforehand.
Interesting.
And maybe not until just before the test.
Interesting.
Or the homework.
Interesting. So that sort of defeats part of the whole purpose of flipping it, right?
Yeah. But I'm not their mother.
Yeah, no, that's right. That's right. Just eliminated the possibility of a great YouTube moment.
Sorry, can you go back?
Hey, how are you? How are you doing? Good. I didn't know you were here.
You didn't?
No.
Oh, I didn't know that Tom was here.
I knew. I sort of vaguely knew Tom was somewhere.
So I dropped by his office last month.
Yeah.
Ah,
Yeah.
It actually took me a while. I was like, I haven't seen you for a long time, so you must have gone somewhere and you're just visiting.
Are you in my class?
Yeah, exactly.
Must look about the same though, apparently. I don't know.
You all look young to me.
I didn't think I aged either, but John says I'm old.
No, I've had a teenager for a while.
I only have a teenager for another
I'll age you.
3 months.
He's almost 20.
Yeah. Can you believe
Hard
that?
to believe.
Yeah.
Hard to believe.
But everybody's out watching the eclipse.
Yes. Including our Colloquium chair. I guess in the Iowa State, you sort of get IA for like the state abbreviation. Okay. I don't know if they did that on purpose. Probably.
No
I'm
idea.
sure they spent
Never noticed
tens
it.
of millions of dollars to design it.
Many consultants were paid, yes, in order
I
to.
think I only heard negative feedback when they switched to that logo.
Yeah.
You'll have that. There's always somebody that doesn't want things to change.
Well, what's amazing to me is the fact that we still are not a very good football team, but they have been actively recruiting, alumni and participation in the games, and so they've managed to generate this enormous buzz around a team which is really not that good, and it's just sort of fascinating to watch.
You gotta appeal to sympathy and do it like the Chicago Cubs.
Ten
Comes
or
in
Big
Big
12?
12.
We're Big Ten.
Yeah.
Big Ten.
Big 10. Big 12.
No, well, okay, I'm sorry, yeah, we're Big 12, which is now 10 teams. Yeah.
Yes, yes.
That has completely thrown me now. I can't keep, right, I can't,
Well, for a while, the Big Ten was 12 teams.
Right.
It's 14 now.
right, and I can't keep track of that. I've allocated that
The
storage.
astronomers have scheduled that eclipse for a later period of time, like 10 o'clock at night or something.
We asked them.
It's difficult to
See, it's
see
over on the
it.
side, yeah. There's live streams from.
Actually, it is very much eclipsed for us by the Earth.
Sure. Every night.
Terrestrial eclipse.
You think we should start? Or I assume Stefan was going to come, since we did see him up on the Earth.
There's also a lunar occultation of Venus if you're in the right spot right now. Somewhere in the South Pacific.
There's one,
Which means that Venus is very close to the sun.
Yes.
there's one honking sunspot too,
Yeah.
Oh,
the size
yeah.
of Jupiter.
Yeah,
That
yeah.
was dirt on the lens, and it's like, no, it's. Wait till it points right at us.
I think Venus will fall in.
Wish they did the 21st century repeat of the Carrington event.
We go ahead and start?
Yeah, I think so. Oh, here comes Pearl. Is Stefan behind you?
Yes, they're all.
Okay, good. Stefan, were there any announcements that we should make before starting? No? Okay.
There are spots on the sun.
There are spots. Okay, so today's colloquium speaker, I've known for a while. We were graduate students together at Yale, so John was a graduate student at Yale, graduated in 1996, and then he went to Iowa State a year later and has been there ever since, working in the realm of high energy, heavy ion physics and spin physics, and today he's going to tell us about nuclear matter.
Okay, thanks, Doug. So the title of my talk today is Baby Pictures of the Universe, Exploring the Nature of Nuclear Matter. And one of the things I hope to show you is that very much like astronomical data like the WMAP Sky Survey uses fluctuations in the temperature of the cosmic microwave background to learn something about the early universe, what we're doing in relativistic heavy ions is actually using density fluctuations in the early stages of collisions of ultrarelativistic nuclei to tell us a lot, actually, about the property of the matter that's created in these collisions. Now, before we actually get started, I understand you're all missing a very important event to attend my talk today, and I certainly appreciate that. So I asked Tom to go ahead and prepare a simulation of what the eclipse actually looks like, so you're not missing anything. I've been assured this is a completely 100% accurate simulation of the eclipse at this point in time. So, let me just start with a brief introduction to what is nuclear physics. So as you might expect, nuclear physics is the study of the atomic nucleus. So if we take an atom and we strip away 99% of the volume of that atom, which is all uninteresting stuff, which is empty space and electrons, you're left with the positively charged core of the atom, which is the atomic nucleus. And typically we'll call this an ion when we're talking about accelerating it because we've stripped off all of the charges, or all of the electrons, and it's positively charged. And of course, as you all know, a nucleus is made up of protons and neutrons. And those protons and neutrons are bound together by what's known as the strong nuclear force. It's called the strong nuclear force because it is in fact one of the strongest it is the strongest fundamental force that we know of in nature. Now, in the late 60s, early 70s, experiments which scattered electrons off of protons and off of nuclei taught us that, in fact, protons and neutrons are not fundamental objects, but they're actually composite objects made up of smaller objects. And those objects took on the name quarks. And so the quarks come in groups of 3. 2 ups and a down quark make a proton, 2 downs and an up quark make a neutron. And they're held together by the exchange of a force carrier, very much in the same way that in quantum electrodynamics, charges exchange photons, and that represents the electromagnetic force. In the strong nuclear force, it's the exchange of a particle known as gluons that provide that strong binding. So what's different about quantum chromodynamics, which is the theory that describes the strong interaction, compared to quantum electrodynamics, which describes ordinary electromagnetic interactions, is that in quantum chromodynamics, quarks come in not one charge, or one charge and an anticharge, but they come in 3 charges. And we typically call these charges red, green, and blue, and you'll see why in a moment. And of course, the force between the quarks come from the exchange of these gluons. Now, the big difference between quantum chromodynamics and quantum electrodynamics is the fact that there are 3 charges in quantum chromodynamics. In quantum electrodynamics, the photon doesn't carry the characteristic charge of the theory. That means that to first order, photons don't interact with photons. In quantum chromodynamics, the carrier of the force, the gluons, actually carries color charge. That means gluons can interact with gluons, and it makes the theory much more rich and much more complicated. So, the theory of quantum chromodynamics describes the strong nuclear force, and the strong nuclear force is what holds the quarks bound together in objects that we call hadrons. And there are really 2 types of hadrons for the purposes of this talk today. And we'll call them baryons, which are collections of 3 quarks bound together in an object. And the reason that we assign to these sort of color charges, red, green, and blue, as the primary colors, is because quantum chromodynamics forces these quarks to be combined into what we call colorless objects, or color singlet objects. So, quantum chromodynamics requires that if we're going to form a proton, it's formed out of 3 quarks in such a way that the net object has no color charge. Likewise, we can form what's known as a meson out of a quark-antiquark pair, and again, quantum chromodynamics requires that these form together in such a way that the net object is colorless. Okay? Why is that? Well, if you look at this in terms of a sort of a simplified classical picture, the quantum chromodynamic potential between, let's say, a quark and an antiquark, if you write this as an effective potential, it has 2 pieces. The first is sort of a 1 over r term, right, which should look familiar to everybody as being the same kind of potential that you get out of quantum electrodynamics when you have the exchange of photons between charged objects. And so that 1 over r portion of the potential basically provides a confining potential. That allows you to have bound states of quarks and antiquarks. Okay? Now, what it also means is that if this coupling constant here is small, at short distances between the quark and the antiquark, the strong interaction isn't actually that strong. It's actually rather weak. And at short distances, one can do calculations in quantum chromodynamics in perturbation theory the same way one does them in quantum electrodynamics. The big difference comes in the extra term that shows up in this effective potential, and that's this term that goes like a constant times the distance between the 2 quarks. There's a linear term in the potential energy between the 2 quarks. And what that means is that the potential rises linearly as you try to separate these quarks to a larger and larger distance. Now, practically that means it takes an infinite amount of energy to separate 2 quarks to infinity, right? What this is representing is the fact that if I try to actually do that exercise, I try to take a quark in a hadron and pull it out so I have a free quark, I create such a large energy density in the vacuum between the 2 that energy density spontaneously creates quark-antiquark pairs that then rearrange themselves to shield the quarks that I was trying to pull out of the hadron. So I create many more particles in a way that reforms everything as a set of color singlet objects. Okay. That's known as confinement in quantum chromodynamics, and that's the reason that no one has ever seen a free quark. They've been searched for. They've been searched for in everything from accelerator experiments to moon rocks and have not been observed. Now, as I mentioned, quantum chromodynamics is an extremely difficult theory to work with. And in fact, while in some regimes one can do perturbative calculations very much like you can do in quantum electrodynamics, for most of what we're interested in, and particularly for this aspect of confinement, right, this long distance piece in the potential makes the interaction become extremely strong. And perturbation theory is no help anymore. In fact, we have computational tools, analytic tools that are approximations to QCD, but we can't do analytic calculations in full quantum chromodynamics, right? What we can do, however, is we can do computer calculations, simulations of quantum chromodynamics. In fact, the full theory by discretizing space-time, doing calculations on this lattice of discretized space-time, and then extrapolating to zero lattice spacing. And those calculations are complete and rigorous calculations of quantum chromodynamics. Now, we can't calculate everything in lattice gauge theory, but we can calculate some interesting quantities. And one of the things that we can calculate is this effective potential that I showed you before between two quarks. Okay? Now, so what this is a plot of now is that same effective potential scaled in units of what's called the string tension. So don't worry about that. And here you see at zero temperature, you see that same potential I showed you, which has the rise in the potential energy to infinity. One of the things that you can do in lattice QCD is you can change the temperature. So you can ask yourself, what happens now if I change the temperature in which this potential is embedded? And what you find is, as you change the temperature in the theory, this rapid rise, this linear term in the QCD potential, is actually tamed and begins to turn over until at some critical value, at some critical temperature, it becomes flat. And once it becomes flat now, it no longer takes an infinite amount of energy to separate a quark and an anti-quark to infinity.
Can you say whose temperature you're talking about?
I will, actually. So the temperature at which that occurs is about 150 MeV. And for those of you who are not familiar with dealing with temperatures in energy units, 150 MeV is about 10 to the 12th Kelvin, right? About 1 trillion degrees. Okay? So it's hot, but lattice QCD predicts that this phase transition, and it is a phase transition, should happen. And this is a phase transition between confined QCD, where the quarks and gluons are confined to occupy a very small region of space, about the size of a proton, to where the quarks and gluons will be free to roam over a large distance in space.
Are you thinking of some gas of this kind of material is hot like that?
Yeah, and I'll actually talk about that. One of the key issues is whether or not it's a gas or it's something else. Exactly. Now, the energy density that this corresponds to is about 1 to 2 GeV for cubic Fermis. And again, for those of you who aren't used to these energy units, a proton is about a GeV and has a radius of about a Fermi. So if I could get 2 or 3 protons and pile them so that they completely overlapped in the same region in space, that would be the kind of energy density I would need to trigger this kind of phase transition. Okay? So this matter, that this deconfined matter, is called the Quark-Gluon Plasma. And it's basically QCD matter without color confinement. And so now that we're talking about a different phase of nuclear matter, we can start to ask ourselves, well, what does the phase diagram for nuclear matter look like? And so what I've plotted here is sort of as a function of temperature and density, the sort of phases of nuclear matter, both measured and hypothesized. We know, for example, that nuclei exist at a finite density of particles and at a very low temperature. There are hypothetical regions, which in fact we don't quite know how to experimentally access yet, that if one goes to low temperature but very, very high particle density, very high quark density, that QCD will actually collapse into color superconductor states. What we're interested in studying is this deconfinement phase transition where we have the Quark-Gluon Plasma. And what I'm going to tell you about today is how we've tried to create this plasma in the laboratory through collisions of very heavy ions at ultrarelativistic energies to cross this phase transition, produce the Quark-Gluon Plasma. Of course, it doesn't stay in that state very long because it cools quickly. It crosses back through the phase transition to form hadrons and particles again, and we measure those particles in our detectors, and the distribution and patterns of those particles tell us something about whether or not we entered this deconfined state. So that's the game. Now, this is relevant for lots of reasons, but one of the main reasons is if the early universe, of course, as it expanded from an original singularity, passed through this phase transition at some point in time. And at this characteristic temperature, it passed through this phase transition somewhere around the first microsecond or so, after the Big Bang. And as the universe cooled, we passed through this phase transition where the quarks again became confined into neutrons and protons, and they've been that way ever since. So, what kind of signatures might we expect from the Quark-Gluon Plasma? Well, let's just think about the energy density for a moment. We can apply a statistical mechanics calculation and ask ourselves, what is the relationship between the energy density and temperature for a gas of particles, right? And of course, it turns out that that goes like some constant times t to the fourth, and there's a constant out in front that tells you sort of how many degrees of freedom you have. The more degrees of freedom you have, the greater the relationship, the constant here, relationship of proportionality between t to the fourth and the energy density. More degrees of freedom, more ways to absorb energy density into temperature. Now, if we have hadronic matter, the most common form of hadronic matter is something called a pion, which is a bound state of a quark and an antiquark, and it turns out there are three of them. There's the pi plus, the pi zero, and the pi minus. And they have zero spin. So if we were to have a very dense gas of hadrons, the relationship between energy density and temperature would go something like 3 times this pi squared over 30. And that's mainly because we only have 3 pions with spin 0. So that relationship is not very steep, right? If we happen to excite a quark-gluon plasma, we now have additional degrees of freedom that become available to us. We have color that becomes available to us, so there's 3 colors. We have 2 types of quark that we can deal with. Now, typically you'll hear in high energy theory, a high energy person say, oh, there's 6 types of quarks. Well, there are 6 types of quarks. 4 of them are really heavy. So when I'm talking about the quark-gluon plasma, the only 2 quarks that I'm really interested in are the lightest quarks, which are the up and the down. And then in addition, I have gluons, and because gluons carry color, it turns out there are 8 distinct types of gluon. Actually 9, but one of them's colorless, so it doesn't contribute to the theory. That means that when you take all of these degeneracy factors into account, you find that the energy density for the quark-gluon plasma should rise very rapidly at the phase transition as you transition from hadronic matter to nuclear matter, to QCD matter, to the quark-gluon plasma. And in fact, this is the kind of thing that's indicated by lattice QCD. Lattice QCD can simulate this phase transition, and at the transition temperature, so this 1 is the temperature scaled by the critical temperature, there's a very large growth in the energy density of the plasma associated with the release of these additional degrees of freedom. So, the other thing that you notice is that the Stefan-Boltzmann limit for a non-interacting gas of particles, right, is actually not that far away from the values that lattice QCD seems to be indicating. So you might think that the proper description of the quark-gluon plasma is, as you said, sort of a gas of weakly interacting particles, right? And so that's one of the assumptions that we're going to try to test today. So, in order to do these experiments, what we needed to do is we needed to open up new energy and intensity frontiers to be able to access the dynamics of the quark-gluon plasma. And that's been done with 2 colliding beam facilities. The first was the Relativistic Heavy Ion Collider, which is at Brookhaven National Lab on Long Island. It saw first collisions in the year 2000 and has been colliding ions every year since. And it's an extremely flexible machine with the ability to collide proton on proton all the way up to uranium on uranium at energies, center of mass energies between 7 and 200 GeV. And somewhere in here, certainly at the 200 GeV point, it's believed that we should be well above the transition point for the quark-gluon plasma. Now, the LHC, the Large Hadron Collider, is a machine you're probably familiar with from the search for the Higgs boson. That machine is a little bit less flexible than RHIC, but it has been able to run lead-lead and proton-lead collisions, although at a much, much higher energy. So when we study these collisions at the LHC, we're studying a very high, much higher center of mass energy, and in principle, a much higher temperature, and even further above the transition. What this gives us, in a sense, is a lever arm. we have the ability to explore the QGP phase transition near the transition point and well above the transition point. In order to, of course, make these measurements, it takes not just machines, but it takes experiments. There are two large particle physics experiments at RHIC. That's the Phoenix experiment, which is the one that I work on, and the STAR experiment. STAR is an experiment that uses a time projection chamber to measure charged particles coming out over a very wide range of angles. So they have sort of a full coverage for almost everything coming out of the collision. And this is actually a picture of a central gold-gold event in the detector. The Phoenix detector is a detector that's optimized for more rare probes. So they're looking for things like electromagnetic probes of the plasma that don't happen as often. So they have less instrumentation, but the ability to be much more selective about the events that they record. At the LHC, there are two experiments, the CMS and the Atlas experiment, that were built primarily to find the Higgs, but they can also make measurements in heavy ion experiments. And then there is one dedicated heavy ion experiment called Lattice. So before I sort of give you the story of the Quark-Gluon Plasma, I want to sort of give you sort of the overview, right? So you can sort of put this in context. And you can ask yourself, what's the big picture? What are you really trying to study in heavy ion collisions? What are you really trying to do at RHIC and the LHC? And what we're trying to do is we're trying to understand how things like collective many-body phenomena arise from first principles QCD. And you'll see what I mean by collective many-body phenomena. We're not just studying a set of particles that are sort of interacting incoherently with each other, but there's a coherence to the matter that's formed. I'm going to talk to you a lot today about the Quark-Gluon Plasma and what we've learned about the Quark-Gluon Plasma. And in the process of doing this, we've actually learned some very exciting things about the initial state in these collisions and what gluons actually do when you take a bunch of protons and neutrons and put them together in nuclei. Tomorrow morning, I'll be talking about how we use polarized protons to actually, instead of smashing things together and seeing what comes out, we use polarized protons to actually study the very complicated structure of the proton. So in one case, we smash things and look at the pieces. In the other case, we look very carefully at a system without necessarily completely looking at it in a destroyed state. Okay. So to set the stage, let's talk about what a heavy ion collision looks like. So imagine that you're sitting and you're looking in the center of mass, and you want to see a heavy ion collision. You're in the center of mass, so the two nuclei are coming together in front of you, and they're traveling at 99.9999999% of the speed of light, right? So they look like extremely Lorentz contracted pancakes, right? When these two Lorentz contracted pancakes overlap, that's t equals 0, and at that point, you create a very large energy density, right? You've overlapped these two nuclei and created an enormous energy density in the center of mass. At this point, you generate interactions between the particles, and that energy density sparks the phase transition that you're looking for, right? And this phase transition is really a phase transition of the vacuum state of quantum chromodynamics. So all of a sudden what you're doing is you're generating an enormous number of particles, QCD particles, from the vacuum in these interactions. So that's all of the quarks and gluons that then are generated in this interaction and begin to interact with each other. They interact in an extremely strong way so that sometime between this 0 and 5 Fermis, Fermi is 10 to the minus 15 meters, and it's about the size of a proton. So if you're wondering in terms of time, what's a Fermi? It's the amount of time it takes a photon to travel the radius of a proton. Okay? Extremely short period of time, right? So about 5 Fermis later, this system has expanded to the point and cooled to the point where we're now cooling beyond the phase transition. The matter is going to recondense. It's going to freeze back into ordinary hadronic matter. And so this is what we call hadronization. And so all of the matter reorganizes itself into these color singlet hadrons, and then these color singlet hadrons fly out to our detector, and we measure them in the detector. Just to set the scale for you, a central gold-gold collision can produce something like 10,000 particles within the acceptance of the STAR experiment. Okay? Oh, by the way, by central, I should define what I mean by central. By central, I mean the two nuclei essentially hit head-on, impact parameter 0. Obviously, we look at all types of collisions, from grazing collisions to the most central collisions. The most central collisions, of course, are the most interesting because that's when you create the highest energy densities. So, let me just very quickly go over just a few of the basic properties that we've measured that convince us that we have, in fact, created the Quark-Gluon Plasma in relativistic heavy ion collisions. And let me just start with energy density. So as I said before, you need to reach an energy density of 1 to 2 GeV per cubic Fermi in order to at least be in the region where lattice QCD tells you that this phase transition should occur. And what we can do is we can measure the energy density or approximate the energy density in these collisions by measuring what we call the transverse energy. And so when the two nuclei come together, all of the energy, all of the momentum is longitudinal, traveling along the beam axis. They interact, you get an expanding blast wave of particles, and so some of that longitudinal energy is converted into transverse energy. And you can relate that transverse energy to the initial energy density, what's called the Bjorkian energy density in this collision. And if we measure that transverse energy density for the most central events, what we find is that the Bjorkian energy density is about 5 GeV per cubic Fermi, and in fact this is an approximation, but it's an approximation on the low side. So we created energy densities of at least 5 GeV per cubic Fermi, which is 30 times normal nuclear density, 1 to 2.5 times higher than any previous heavy ion experiments, and significantly above where the phase transition is predicted by lattice QCD. Now, in addition to reaching a high energy density, as I said, we also have to reach a very high temperature. How do we measure the temperature? Well, how do you measure the temperature of anything, right? The temperature, when something is hot, what does it do? Well, it emits photons of a distribution which is characteristic of its temperature, right? And so what we do is we look for the thermal radiation from the Quark-Gluon plasma. And the thermal radiation is an excellent signature because photons don't have color charge. So photons can be emitted and then will escape the plasma without interacting any further. And so the signature of that temperature won't be destroyed by the plasma. So how do we measure photons?
You don't need any electrical dipoles to create photons.
No, we don't need anything like that. So these are basically created within the collision from, quark-bremsstrahlung will create these photons, for example, right? So what do we do? Well, first we start with sort of a control experiment, which is we look at photons created in proton-proton collision. And the photons created in proton-proton collisions happen not from a plasma effect, but they happen from single scatterings between quarks and gluons at very high momentum transfer. This is the portion of QCD that the high energy people, for example, use. And so we can measure that and compare it to these perturbative QCD calculations, and it matches beautifully. So we think we understand our baseline, and then we can go look at what we measure in very central gold-gold collisions. And what we find in gold-gold collisions, we can then compare what we find in gold-gold collisions to the PP result scaled up by the number of ordinary PP-type collisions that we would expect. And out here at very high transverse momentum, it matches the scaled PP result beautifully. Down here at low transverse momentum, what we observe are more photons than we would have expected from the proton-proton result. And this excess is indicative of the thermal photon emission that we're looking for. We can take this excess emission, it can be fit in a variety of different theories which predict the emission of thermal photons based off of the temperature. And although there are error bars around this depending upon how you do the analysis, the initial temperature that's been indicated from the Phoenix analysis is something like 370 MeV, right? So, 3 or 4 times a trillion degrees, right? So again, significantly above the transition temperature. And we're observing thermal radiation from a hot radiating blackbody source. Okay. Yeah. Go ahead.
When you say temperature, do you literally mean temperature or some typical energy? Or in other words, how many times do your constituent particles collide?
That's a really good question, right? So what you're basically asking is, do you believe that this Quark-Gluon plasma is really equilibrated at this point so you can define a temperature? And the answer is yes. We believe it is equilibrated, but one of the mysteries is how it manages to equilibrate so quickly, because the time scale is extremely short.
But how many times do they collide, your gluons, quarks, and all this?
Yeah, and that is exactly the problem.
A couple of collisions should be enough, right?
A couple of collisions should be enough, but if you just take and calculate, let's say in perturbative QCD, how does the energy get redistributed by these soft collisions? And what is the average time scale between these collisions? You find that a few Fermi is just not enough to thermalize the system. And yet a lot of the measurements that we make, and a lot of I'm not showing you here today, really indicate that it's thermalized, right? And I'll get back to that in a moment, because it's telling us something about the initial state. That the initial state is not properly described as sort of discrete, incoherent quark-gluon collisions. But there's something else going on there. Okay?
But you're getting real black body radiation?
We're getting thermal emission from the plasma. We believe we're getting thermal emission from the plasma. I'm sorry?
You don't measure the spectrum, you get a temperature.
What you measure is something that's sort of equivalent to measuring the spectrum, which is measuring the emission as a function of the transverse momentum of the photons, right? And that slope of the transverse momentum is directly related to the temperature, and that's actually how we extract the temperature from the data. Okay, now something else that we measured, which actually came as an enormous shock when the first data was taken at RHIC, was this elliptic flow of particles. And so what do I mean by elliptic flow? Well, let's think about a collision between two nuclei, which is not a head-on collision, but it's actually a grazing collision, right? And so that means there's a finite impact parameter between these two nuclei as they pass by. That impact parameter can define what we call a reaction plane, okay, the plane in which this collision occurs. And the overlap region between the two nuclei then is actually an almond-shaped region, right? It's asymmetric with respect to this reaction plane. And so what's going to happen? Well, what happens is if you create quark-gluon plasma in this region with a very high energy density, there will be a pressure gradient. And the pressure gradient will be smaller in the long direction of the overlap region and larger in the short direction. And so when this expands, it will actually force the matter in plane harder than it will force the matter out of plane. And that should result in an azimuthal anisotropy of the particle emission with respect to the reaction plane. What we measure is we measure the particle distribution, the number of particles coming out as a function of energy and transverse momentum with respect to this reaction plane, and we pull out this second Fourier component. We basically do a Fourier analysis of the particle distribution, and we pull out this second Fourier component, and we call that V2. Now, what this looks like, so you can sort of see in this simple simulation here, what does this look like? Well, you can see the almond-shaped overlap region starts like an almond, but as time goes on, you can see that the energy density in the center is pushing things out in plane more than it's pushing things out of plane. And in fact, when this was measured early on in the first data at RHIC, the fact that this azimuthal anisotropy was as large as 20, 30, 40% was an enormous surprise. Right? What it means is the matter is flowing in a coherent way, that you really can almost describe the matter that's created in here in a hydrodynamic way. Now, what was measured then was to say, great, let's measure this elliptic flow for every particle we can think of, right? Because somehow this has to be telling us something. And so this elliptic flow, this V2 parameter, the second harmonic of the particle azimuthal distribution, was measured for pions, kaons, the phi meson, which is interesting because that's strange quarks, protons, antiprotons, deuterons, antideuterons. And it's plotted here as a function of the amplitude of that elliptic flow versus the kinetic energy of the particles. And you plot them all in the same plot, and everybody went, I don't get it. Right? Because even though they're all showing elliptic flow, they're all showing a different pattern of elliptic flow, right? And actually, this went on for about a year, where this was extremely confusing to people in the field. And then somebody got the bright idea that, well, wait a minute, maybe we're thinking about this wrong. Because if it's the hadrons that are flowing, then they should all have the same pattern. But we don't think it's hadrons that are flowing. We think it's actually the quarks that are flowing. And if it's the quarks that are flowing, we really should plot this in terms of the kinetic energy per quark. So if it's a baryon, we divide it by 3. If it's a meson, we divide it by 2. And we should plot the elliptic flow, not the elliptic flow at a hadron, but the elliptic flow per quark. And when you do that, all of these particles lie on the same universal curve, right? And so we've created matter with a very high energy density. We've created matter that is well above the transition temperature, well above the trillion degrees required, and that matter appears to flow hydrodynamically. And the degrees of freedom, at least at the point at which it freezes out to hadrons, appear to be quarks, right? So that's very strong evidence that what we've created in these RHIC collisions is, in fact, the quark-Gluon plasma. Now, as it turns out, this split between different particle species, yeah?
Why you cannot consider the contribution from gluons?
What, the contribution from gluons where?
I mean, in these diagrams.
Well, because none of these hadrons, right, have what you would call a valence gluon, right? In fact, there haven't been any particles observed that have sort of valence gluons, which is actually a big mystery in QCD, because lattice QCD really predicts, for example, things like glue balls should exist. And there are experiments at JLab, GlueX, for example, that are looking for this. None of these particles have what you would call a valence gluon, so that shouldn't show up as a degree of freedom. If you could measure a glue ball and put a glue ball on this, I'll make a prediction. If you find me a glue ball and measure the elliptic flow from these collisions, I would bet you, and you treat it as a degree of freedom, it'll lie on that curve. Okay, so as it turns out, this different pattern and the fact that the quarks are flowing actually turns out to be a very strong signature of the hydrodynamic flow, because you can treat this separation essentially as a signature of the quark flow. And so what was done shortly after this was realized was to say, great, the matter looks like it's flowing hydrodynamically. Let me treat it as though it's a gas or a fluid and apply the equations of hydrodynamics. And what I'll do is I'll allow the matter to expand in individual cells. And in the cell's rest frame, when that cell drops below the transition temperature, I'll use a prescription to turn it into hadrons. And then I'll boost from the rest frame of that cell back into the lab frame. And that will predict the distribution of particles, and it will predict this mass splitting that I see for different kinds of particles, right? And in fact, as it turns out, those very simple models fit the data very, very well, right? So this is sort of a characteristic fingerprint of a flow pattern. And around 2005, this led to the statement that, well, the Quark-Gluon Plasma is actually a perfect fluid, right? What do I mean by perfect fluid? What I mean by a perfect fluid is these hydrodynamic descriptions did not include any viscosity, right? So they were relativistic hydrodynamics with no viscosity, right? Now, that seems a little strange, right? The viscosity, of course, should be small, but why would the viscosity be exactly 0, right? And in fact, can we take this data and can we learn anything about the viscosity of the Quark-Gluon plasma? So very quickly, let me just talk briefly about viscosity. So, and let me just do this in analogy to something everybody's familiar with, honey, okay? So everybody's familiar with the honey and the fact that, you know, for most types of honey, if you heat up the honey, it actually becomes less viscous and flows more easily, right? What is that telling you? Well, what that's telling you is that the change in temperature has changed the interaction between the long hydrocarbon molecules in honey such that the honey flows more easily and with less viscosity, right? Likewise, if you cool it down, you've changed the interactions again. The only thing I want you to take away from this analogy is that interactions between particles, especially long-range interactions between particles, are important in hydrodynamics in determining the viscosity. So let's ask ourselves, what can we learn about, say, the viscous flow of a gas or a fluid of particles? And what I'm going to use is I'm going to use a particular way of describing the viscosity in terms of the shear viscosity, or what's also known as the dynamic viscosity. And for those of you who haven't encountered this before, you can think of the dynamic viscosity, the shear viscosity. Let's say I take two plates and I trap a fluid between them, and then I start moving this plate with a certain velocity. That will introduce a velocity gradient in the fluid, and that will result in a retarding force, which is trying to oppose the motion of the plate that I'm pushing along at a constant velocity. The relationship between those two is what's known as the shear viscosity. Okay? It's a measure of dissipation. How efficiently does the medium dissipate the energy that I'm trying to put into it? Okay? So, let's do a simple exercise. What I've done here is I've defined a fluid flow with two regions. In the top region, I've given the fluid particles a very large mean momentum along the x-axis. In the bottom region, I've started out the particles with a much significantly smaller average momentum along the x-axis. And so what I do is I then let this go as a function of time, and what I've done is I have absolutely no interactions between the particles. So you can think of this as an ideal gas, right? There's no interactions between the particles, and as a function of time what you see is that the mean momentum in each region comes down to the same average value. What's happening here? It's diffusion, right? There's no interaction between the particles, so what's happening is particles from the lower region are moving into the upper region, and particles from the upper region are moving into the lower region, and the two regions are mixing, right? In some sense, the characteristic fingerprint of these two regions is being dissipated, and it's being dissipated very quickly. Now, that might seem strange. It's being dissipated because there are no interactions between the particles, right? It's not that there's a lot of interactions and that dissipates things. It's exactly the other way around. Let's see what happens if we introduce strong coupling. If I now introduce a very strong coupling between the particles, so they have a very strong interaction between the particles, what I find is that the mean momentum along the x-axis converges much more slowly. And the characteristic fingerprint of these two regions in terms of their mean momentum lasts for a much longer period of time. Why is this? Well, the medium is less dissipative, right? At the interface here, where the particles can interact with each other in different regions, certainly one particle sees the interface, but it also sees all of its neighbors from the other region behind it, right? And so the strong interactions actually act to reduce the dissipation of the medium. It's almost counterintuitive. So what you're seeing here is when you have inhibited diffusion, what you really have is a very small viscosity. The medium is not dissipative. A small viscosity is what you need for the perfect fluid. But that leads you to the conclusion that the Quark-Gluon Plasma, instead of being a weakly coupled gas, is much more properly described as a very strongly coupled fluid. And that's a major surprise, right? Stunned the theorists, and in fact, there's no good explanation for, or no good description for why the Quark-Gluon Plasma is strongly coupled. But it appears to be strongly coupled, and I'll show you a little bit more about that here. So let's concentrate on this shear viscosity, and in fact, I'm going to change a little bit. I'm going to concentrate on the shear viscosity to entropy ratio, which is the kind of thing that theorists like to calculate. And what do you find? Well, for some ordinary materials, let's say helium, nitrogen, water, what you find is the shear viscosity to entropy ratio is always a minimum near a phase transition in that material. And so the typical dip here is the gas-liquid phase transition, but in fact in helium you can even see an inflection in the shear viscosity to entropy ratio at the superfluidity transition. Okay? So how low can the shear viscosity to entropy ratio go? Well, as it turns out, there's a prediction from string theory. Do I have any string theorists in the audience? Okay. Then I won't tease too much about string theory actually producing a numerical prediction, but it did. And the prediction from string theory is that the absolute quantum lower bound for this quantity, the shear viscosity to entropy ratio, is 1 over 4 pi. It cannot be smaller. And so the question we want to ask is, well, what is the shear viscosity to entropy ratio for the QGP at 1 trillion degrees? Okay? How are we going to determine this? Well, remember, what I said, one of the key things is that a low shear viscosity means that the medium does not dissipate fluctuations within the medium very quickly. The characteristic fingerprint of early time is maintained for a long time throughout the evolution of the medium. So what happens if I now take two nuclei and I collide them, and I'm looking here at a collision which is, let's say, not a central collision? There will be density fluctuations. there will be density fluctuations because the nucleons are not evenly distributed at a snapshot in time throughout the nucleus. They're randomly distributed. And so there can be density fluctuations where you have higher density and density fluctuations where you have lower density. When those nuclei overlap and collide, you will have density fluctuations in the matter that's created. On average, the nucleus will have, the overlap region will have this almond shape, but collision by collision, there will be density fluctuations, and those density fluctuations will survive to the final state because the medium doesn't dissipate them very efficiently. Okay? So what you end up with is that these fluctuations in the initial positions and fluctuations in the position of the initial nucleons will generate not just a harmonic V2 component, but it'll generate a V3 component, it'll generate a V4 component, it'll generate a V5 component. All driven, by these different Fourier moments, all driven by fluctuations in the original nucleus. So this is what leads to this idea of a detailed fingerprint of early time. And those fluctuations and the fact that they survive and the degree to which they survive can be used to extract the shear viscosity to entropy ratio. And in fact, that's the kind of thing that has been done by theorists by including viscosity in their calculations and using viscosity as a parameter to fit not just the elliptic flow, but the higher order V2, V3, and the V5 moment. Okay? And the result of that is that when one fits the RHIC data at 200 GeV, what one finds is the shear viscosity to entropy ratio that best describes all of these components is about 0.12, which is about 1.5 times the quantum lower limit. So in fact, the shear viscosity is very low. It's only 50% larger than the lowest it can possibly be. Now, you might expect at the LHC, where you're at higher temperatures, remember it's always a minimum right near the phase transition, that the shear viscosity would be larger. And in fact, the data for the harmonic components from the LHC show that it tends to prefer a higher value of the shear viscosity, right? About 0.2 or about 2.5 times the KSS bound, or the string theory bound. So what we've done is we've used the fluctuations in the quantum fluctuations in the overlap of the nuclei as a probe to actually probe the characteristics of the matter that's created in these collisions. And that is only possible because this matter turned out to be completely different from what we originally thought it was going to look like. So this is what's referred to as the perfect fluid. The discovery really is that the Quark-Gluon Plasma acts as a near-perfect fluid, and the precision in terms of determining the properties of that fluid comes from the prediction of flow patterns. And those flow patterns combined with hydrodynamics allow you to determine the shear viscosity to entropy ratio. But there's a lot of things hidden here. One of the things that we've already touched on is how does the system equilibrate so quickly? All of these hydrodynamic models absolutely require that the system equilibrates very quickly, right? Much more quickly than would be possible if you were to just account for individual collisions between quarks and gluons, right? So there must be something going on here. And that something is, what really is the initial state? Do we really understand the initial state for these collisions? The other question that you can ask is, particularly near the phase transition, are the degrees of freedom really the quarks and gluons? Or are there quasi-particle degrees of freedoms? Quasi-particles may be quasi-bound states. Or are they truly free? If they're interacting strongly, if there's a strong interaction between the particles and the medium, is the right description then as a set of free quarks, or maybe loosely bound quasi-particles or resonances within the medium? And to understand that, we need to probe the medium structure in more detail. So let me address this first issue in terms of what is the initial state. So in order to understand the initial state, what we need to do is we need to do a control experiment. When we do an A+A collision, we're generating an enormous amount of particle density, enormous amount of energy, and we believe that we've crossed the transition into the plasma. But that then confuses any initial state effects with any final state effects. So what we need to do is we need to probe a heavy nucleus, but we need to probe it in a way where we don't think we're going to create the quark-gluon plasma. And we do that with deuteron or proton nucleus collisions where we don't believe that we create a large enough energy to create the quark-gluon plasma. So, very quickly, what have we learned from doing deuteron-gold collisions at RHIC? Well, from deuteron gold collisions, the key thing that we look at is we look at something called a ratio, a nuclear modification factor. And the nuclear modification factor is basically look at a multiplicity or a cross-section in deuteron gold collisions, and then take that same measurement in pp collisions and scale it by the number of binary pp collisions that we think we get in deuteron gold, and you can model that with something called a Glauber model, and divide these two. If there are no nuclear effects, or in other words, if a nucleus just behaves as an incoherent superposition of nucleons, that ratio will be 1. If there are nuclear effects, that ratio will deviate from 1. And so, for example, these are measurements for the production of pi zeros and charged hadrons going sort of a little bit forward, not quite in the center of mass, but going a little bit forward. And what one finds is this nuclear modification factor, in fact, is hugely suppressed by a factor of 4 or 5. Particularly at low transverse momentum. And of course, low transverse momentum is where most of the particles come from. So what this is telling us is there's something about the initial state that we don't understand. Something about the initial state in nuclei that we don't understand. You see this in a variety of other measurements as well. Phoenix sees this in looking at correlation measurements, looking at J-psi particles, and we even see a difference in this if we look at collisions between nuclei that don't produce many particles and collisions that are very violent to produce many particles. Those that are very violent to produce many particles show a stronger suppression. Okay? So what's happening here? Well, to understand what's happening here, let's go back and take a quick look at the proton. Yeah?
What is the time scale when you refer to the initial state? I mean, initial state is how long after the collision?
The initial state is before the collision. Before the collision. So I'm asking, what is the initial state in terms of the distribution of quarks and gluons in the nucleus prior to their collision? Right? So in order to understand this, let's go back and take a look at protons for a moment. You can measure the distribution of quarks and gluons inside protons with something that's called deep inelastic scattering. Basically, you bounce electrons off the proton. And what's typically done is to measure the distribution of these particles as a function of the fraction of the proton's momentum that they carry. Okay? And so this is done here. Now, this is a highly logarithmic scale, and this is just one example for the distribution of up quarks, down quarks in the proton, and not surprisingly, the up and the down quarks peak at about 1/3. They're the valence particles, right? They sort of give the proton its character. But what you find is that measurements that tell you how many gluons you have rise very rapidly once you get below this valence region. And in fact, when I get into momentum fractions of 1% or fraction of a percent or so, the proton looks like it's all glue. In fact, this is rising so quickly that it threatens unitarity. If I integrate over this, I should get the fraction of the momentum that's carried of the proton that's carried by the gluons, and that turns out to threaten to be infinity if it grows like this. Okay? So something must be happening. Something must be taming this growth of gluons, especially at small x. And this is where the fact that the gluon is different comes in again. The gluon carries color charge, so it can split into 2 more gluons, or 2 gluons can combine and form 1 gluon. Okay? And so what's happening here is this growth is driven by high x fraction gluons splitting into lower x fraction gluons. But if you think of what happens as I go lower and lower and lower, there are more and more and more gluons, the density goes up and up and up, and pretty soon there's a competing process. And that competing process is the recombination of gluons. So it was realized that the recombination of gluons will have to tame this at some point. We don't know where. It will have to tame it at some point. And one model of that taming is that these gluons, when the occupation number becomes so high, they become so dense, you can basically describe them in terms of a classical field. And that classical field looks like a glass, and that's referred to as the colored glass condensate. And one of the predictions of this theory is that if you look at any hadronic matter, and you look at it at the right scale or below the right scale, it all looks the same. It all looks like this glassy, correlated state of highly condensed gluons. Doesn't matter whether you're looking at a proton, a neutron, a pion, whatever. It all looks the same. It's one of the predictions of this theory. Now, the interesting thing is what happens when you take a proton and you put it inside a nucleus. When you take a proton and you put it inside a nucleus, what happens? Well, all of these small momentum fraction gluons, small momentum fraction means small momentum means long wavelength, right? So the wavelength of these gluons is actually longer than the proton that they are part of. And when I pack them together in a nucleus, the gluons from one proton can talk to the gluons from the other. Okay? So something funny happens when you put all of these particles, all of these nucleons together in a nucleus. And what happens is you get an amplification of this desire for the gluon matter to condense. And it condenses at a much, much higher scale. So nuclei actually act as an amplifier of these high gluon densities. And so while this might be difficult to see in a proton because it happens at very small x, it happens at much, much higher x in heavy nuclei. And that's what's relevant to the initial state. So if you look at what happens in a heavy ion collision, now plotted in a different way, what appears to be happening is you're colliding two pancakes that now don't look like just a bunch of frozen pinpoint particles. They actually look like sort of two pancakes of dense classical fields of gluons. And when those dense classical fields overlap, they shatter each other. And they shatter each other in such a way that they pull flux tubes of energy density between them. And that creates what's known as the glasma, the glassy plasma initial state. Why is this important? It's important because this interaction here and sort of the fact that there's an enormous amount of coherence in the initial state means that the system equilibrates much, much, much faster. So that's the answer to why the system equilibrates. And it's an interesting answer because not only did we learn something about nuclear matter above the phase transition, but we think we've learned something about nuclear matter and this colored glass condensate in the initial state, in nuclei. Okay? Now, very quickly, let me just show you one more thing, because this is great, because it sort of calls into question everything I've told you in the rest of the talk. So,
Can I ask you a question?
yeah.
What is the time scale for the existence of the plasma?
So the glasma is on the sort of the 1 to 2 Fermi time scale, right? That's the point at which the glasma shatters, these flux tubes are pulled out, and then they shatter into a hydrodynamic distribution of particles. So, now, proton-lead collisions have also been measured at the LHC, and remember the energies here are much, much, much higher. Right? And so what is extremely exciting about these collisions at the LHC is what they see in a very small class of events. So if you take proton-lead collisions and you take the most violent collisions that produce the most particles, and you say, what do those collisions look like? Well, in terms of distribution with respect to a reaction plane, they actually see that V2 modulation. That modulation that looked like hydrodynamic flow. And not only do they see it when you look in the center of mass, if you look at particles that are moving forward and backwards from the center of mass in the collision, they see this correlation stretched out like a longitudinally expanding plasma. Okay? Totally unanticipated. Why would this kind of observation show up in, say, proton-lead collisions? Well, one possibility is because this colored glass condensate allows for a hydrodynamic expansion across what's known as pseudo-rapidity, across this velocity range. What's interesting is this has also been observed now in the most violent proton-proton collisions at these energies. The most violent collisions at these energies are probing the smallest X ranges. So it's possible that at the LHC, we're now looking at high enough energies to probe this glass condensate in proton-proton collisions as well. Okay? But this needs much, much more data to be fully worked out. Okay, let me, I'm going to skip over a few things because I'm running a little late on time here. One of the things that we want to do is we want to be able to study this shear viscosity to entropy ratio in more detail. And one of the ways to do that is to probe the plasma as it expands. And something we can look at is the production of heavier quarks, like charm quarks and bottom quarks, which are born in the initial collision and then have to propagate through the plasma to get out, right? And that means that there's a coupling between these quarks and the plasma. And as it turns out, if you ask yourself, how much do we really know about this shear viscosity entropy ratio and its evolution near the critical point, these hydrodynamic fits, they all agree the minimum is close at this critical point, but they don't agree with the temperature dependence of the shear viscosity to entropy ratio. And that we can get by comparing this Q hat, which is the coupling of these heavy quarks as they propagate through the plasma and lose energy. And as you might expect, if the shear viscosity is small, the interactions between the particles are large. That means if I try to shoot a particle through it, that particle is going to interact and lose a lot of energy. So there's an inverse relationship between this coupling constant and this shear viscosity to entropy ratio. And that's one of the things that we want to explore. One of the ways that we plan to do this is with a major new detector project at RHIC, which basically allows us to look at jets of particles coming from these bottom quarks or these charm quark events. And so what we're basically doing, it's almost like shooting a bullet through the plasma and looking at how it gets deflected or whether it comes out at all. Just to give you an idea of the timescale for these sorts of things, RHIC is running right now. We'll be running next year with a new set of upgrades. I'll tell you a little bit about the MPC-EX pre-shower upgrade tomorrow's talk. They'll run again in 2016. There will be a year shutdown, and then there will be a low energy scan. And the low energy scan is basically to look at where the phase transition actually turns off. So can we actually scan low enough in energy to turn off the phase transition? There will be another year shutdown, and then there will be upgrades to STAR and Phoenix. This S-Phoenix upgrade is one of those that I told you about. And then there will be another 3 years of running where we try to probe the properties of the plasma now in much, much more detail. At the LHC, this is really dominated by proton-proton running for the Higgs, and they're just entering a large high-energy running for the Higgs. But there are sort of 1 month running periods that are scattered throughout this, along with upgrades that will bring new and exciting data from the LHC. The ultimate goal is to build something called the Electron Ion Collider. I won't tell you anything more about that. If you want to know, you can ask in a moment. So very quickly, let me just finally address one of the comments that I get a lot, which is, and it's actually a lot from people in other fields who want our funding, but what is this all good for? Why do I want to know this, right? What do I gain from studying the strong interaction and really studying it to the point where I really understand it and I've mastered the strong interaction? Well, let me tell you by analogy. And so we started out talking about QCD in analogy with QED, the electromagnetic force. And so let's just take a look at sort of what is our path or progression of our understanding of the electromagnetic force. And so one can sort of start out with maybe the earliest observation of the electromagnetic force in atoms, being, say, the Fraunhofer lines, which were observed in 1814. And following that, there were a set of precision measurements which made contact with theory, which predicted new measurements, which then made additional contact with theory that allowed the theory to evolve, so that eventually there was a complete understanding of quantum electrodynamics, as was elucidated by Feynman in 1948. From the point that we had quantum electrodynamics, we could now calculate the structure of the hydrogen atom from first principles. No models, no approximations. We could calculate the structure of the hydrogen atom from first principles. Okay? What did this lead to? Well, all the way now in 2012, 2014, take a look at everything that's come out of our understanding of quantum electrodynamics. We understand complex atoms and molecules. We're now capable to do protein folding simulations, which are really complicated interactions between the electromagnetic binding of different elements in a large complex protein. And that's just the beginning. Right? There's all sorts of applications which are just now starting to come out of quantum electrodynamics. But this has been a 200-year process, and many applications of QED have really only started to become relevant about 60 years or so after the establishment of QED. Let's take a look at where we are in quantum chromodynamics. In quantum chromodynamics, where we are right now is we're still in this stage, where we need to make finer and finer precision measurements that connect to fundamental theory, which then make new predictions that we can then again test with finer and more fundamental measurements. What is this going to mean? Well, once we master quantum chromodynamics at the same level that QED was mastered, we can, in principle, for example, do nuclear structure calculations ab initio from first principles. Not just nuclear structure, nucleon structure, right? It may be possible to engineer forms of hadronic matter that are not observed in nature any longer, right? What sort of applications will that have? I don't have the slightest clue, right? But what I do know is it will probably be extremely exciting, okay? So, the idea is to confront QCD with precise measurements and develop an ab initio understanding of nuclear and nucleon structure, and that will eventually, that is mastery over one of the forces of nature, and that will eventually lead to applications that I'm certainly not imaginative enough to think of right now. So, let me just summarize. So what I've told you about today is the discovery of the quark-gluon plasma, and the exciting discovery that in fact it's not a gas of weakly interacting hadrons, but a fluid of very strongly interacting hadrons with a shear viscosity and entropy ratio that's near the predicted quantum lower bound. We obtained this, of course, from a precision description of the flow, and that's resulted in sort of this little bang standard model. There are new questions about what's happening in small systems and our understanding of the initial state in these collisions, and that's feeding back into more precise models and more precise understanding of what we're measuring in these collisions. And over the next decade or so, there are going to be new opportunities to discover more about not just the properties of the QGP, but the how and the why of why the QGP has those properties. Thank you. And by the way, just so you're not missing it, this is what the eclipse looks like right now. 10 minutes ago. Well, I'm an experimentalist, so there's always an error bar on these things. Yeah.
So do you want to come back to the early universe?
Sure.
And say what you've learned at RHIC and how that gives us some better understanding of what happened in the early universe?
Yeah, that's a really interesting question. I'm not even sure I'm qualified to answer that. We've had a lot of discussions with cosmologists about, well, what does it mean that there is this phase transition, right? And the matter beforehand was not a hot gas, but was actually flowing like an almost non-viscous fluid, right? And the answers we've gotten are sort of, I'm not sure, I don't know. I think that that's one of the aspects that sort of needs to. It's not clear, right? It's not even clear to me that it has major observable consequences. Most of the phase transitions that cosmologists are interested in happen much earlier in the evolution of the universe, and this is sort of that boring one at the end to them. So I'm not sure I have a clear answer. Not sure it's also been completely absorbed by the cosmologists. Yeah.
You have skipped some slices. My question may be related to that. You know, recently there's a so-called chiromagnetic effect
Yes.
in these things.
Mm-hmm.
Yeah.
Okay, so the idea is that if you think about what you have, if you have two ultrarelativistic nuclei that are sort of barreling towards each other, right? Well, what you have are two highly charged objects, right? Two highly charged objects that are moving, right? And that can generate an enormous magnetic field in these collisions, right? Scales that are just many, many orders of magnitude above what you could ever conceive of generating in any other mechanism. And so there are some theoretical predictions that what that results in is, for example, a separation in the flow of charged particles. Positive charged particles tend to flow in one direction, negative charged particles will want to flow in another, for example. There is some data from the star collaboration that would seem to indicate this. That data is highly controversial and highly speculative. And one of the weaknesses of the models right now is that the calculations that are done to say, yes, there should be this effect, well, the big thing that they calculate that the relaxation time is larger than you would expect. But they have not merged that model with, say, these relativistic hydrodynamic calculations to predict what the signal should be. So that's really interesting, and I really hope they do that, right? Because I think that's critical. I got a lot of questions about the star data. It would help a lot to have experiment or theoretical predictions alongside it. Yeah.
What happens to the charge on the proton when those little guys come apart? I mean,
When the proton busts up?
yeah.
So
Where's
the
charge go?
quarks also carry electromagnetic charge. So the up quarks are plus 2/3, and the down quark is minus 1/3. So the charge doesn't disappear, it's just carried off by the quarks.
Okay.
Yep.
So but you don't need that electromagnetic interaction when you're calculating thermodynamics. It's too weak.
Well, exactly. That's exactly right. The strong force, especially when the strong force is sort of released in all of its glory on the other side of the phase transition, is so much stronger than the electromagnetic interaction that it's only important if you're looking at electromagnetic probes, and then it's really only important for calculating the initial rates of these things. But it's negligible for any of the hydrodynamics or the thermodynamics.
Sir, this is kind of naive. So you told us the temperature scale for the transition. What are other energy scales involved in this business? Can you compare the temperature to, I don't know, mean interaction energy of stuff in plasma and things like that?
The one thing that you can compare it to is there's a fundamental scale in QCD that divides what we call the hard scale and the soft scale. The hard scale is basically where the calculation is such that perturbation theory works, and the interaction between the two particles is weak. And the soft scale is where perturbation theory breaks down and the interaction becomes strong. You can also relate this to distance scales, right? And that's called lambda QCD, and lambda QCD is something like 140 MeV. So the phase transition temperature is very similar to the scale at which the interactions go from being weak to being hard, or go from being weak to being very strong, or hard physics to soft physics.
But then it also tells you that your plasma has to be strongly coupled, right? Because basically if you just reach that temperature, you're guaranteed, to have kinetic energy be similar to potential energy. That's just like in water.
I think that's a true statement now, with the benefit of hindsight. It was certainly unexpected. Theory, in particular, has made enormous advances over the past decade in dealing with calculations that are in this sort of crossing the hard and soft regime. At the time, say in the early 90s, late 80s, when this was hypothesized, nobody was really willing to do calculations that they would show publicly in that regime. And so the idea was, it was a very naive one, but the idea was, well, once you cross over this phase transition, you must be in this regime where the interactions are weak, alpha is small, and it's just going to behave like a weakly coupled gas. You're right, with hindsight, that was extremely naive. But that's why we do these experiments, right?
One of your slides showed these density fluctuations on the same picture with the background, that one.
Yep.
What's the correlation there?
So it may be a weak one, but the idea is that the WMAP survey, what you're really looking at here, right, are temperature fluctuations, very minute temperature fluctuations in the cosmic microwave background.
Coming from density fluctuations.
But coming from density fluctuations in the early universe, right? And so these fluctuations sort of survive in the cosmic microwave background. The fingerprint of them survive, right? And again, in a similar way, the fingerprint of the density fluctuations in these heavy ion collisions actually survive to the final state distribution of particles. And
The origin of the density fluctuations is completely different.
yeah, absolutely. Absolutely. Absolutely.
And one we understand and the other we don't.
They're just density fluctuations, and beyond that, the origin is completely different. But I think the idea is that you learn a lot, right, by understanding how these fingerprints of early time, when you find a place where you can get them, right, actually tell you an enormous amount about the dynamics involved.
Any other questions? I guess it's time to speak.
before the first year graduate students go, I've been asked to make sure that you look at the Canvas email messages that you got about the graduate research fellowship proposals. And I hope all of you are preparing them because it's due in another few days.
Might be. I've got like 2 of them. I stick them. I've got one in my bag and one in my office, and that way I'm never without one.
Oh, 0400. Okay, so they've got a new one now, I guess.
Do they?
I was just doing trying to find one that's Bluetooth instead of USB. Logitech does not make one.
Boy, you know, I gotta say, the experience I have with Bluetooth is it gets interrupted easily, and I don't think with a Bluetooth device I could have easily worked from over here. I would be surprised. I would be surprised. But so I would be a little nervous about a Bluetooth device.
I've got a Bluetooth presenter mouse with a built-in.
Does it work?
I haven't tried it recently to see how far away it can get.
Yeah.
It's decent. But it's also it's shaped like a little pin. It recharges on USB instead of having batteries.
Oh, yeah?
Very compact, very
Well,
friendly.
you know, I think I've got the pen for this, and I think I could actually use the pen for the same thing. I've just never actually taken the time to sit down and figure out how to do it. You're always too busy, you know. Oh, thank you.
I could watch those simulations of the flows. Screensaver on that.
Yeah, unfortunately,
About elliptical flow back at RHIC. It must have been 96, 95.
right, so they were measuring elliptic flow. They were measuring V1 and V2 in AGS experiments, right? And so at AGS energies, you get actually a V1 component because the collision is sort of slow enough that you get sort of a bounce off, right? So you could see this V1 bounce off pattern in the protons. And the question was, was there any V2 that you could see, right? And you saw some, right? But the problem with it was the magnitude of it was exactly predicted by purely hadronic cascade models. Right? So if I just make a model which assumes no plasma, just interactions between hadrons, and I let it run, it gave me the bounce off and it gave me the flow perfectly. Right? So it told you something was happening, but it had no obvious connection to, say, a plasma state. And so the prediction actually from these was, we'll know we have a plasma when the elliptic flow disappears.